All right, so we're going to take a look at our next lesson in the list of what we've got for our force list. So in the previous lessons, recap of the unit, we took 2 lessons spread across basically about 2 hours or so. The first one dealt with introducing the concept of dynamics, the background of Newton's laws of motion. We did Newton's first and second law in that lesson. And then we did, in the second lesson, we looked at Newton's third law and introduced the idea of free body diagrams. And then in our third lesson, the one just before this, we actually introduced the force list that we are now working our way through, and we talked through the important applications of the force of gravity. We're going to build on those. We're going to see in all of our examples, including this one, we're also going to have the force of gravity, and we're going to continue working with that. But now we're going to the next one in our list. This one is called the normal force. Now, I have a lot of students that call this the natural force or something like that. I think it's something that's easy to forget, but I will try and repeat this. It's a normal force, and we'll get used to it more and more as we go through our studies and make certain that we're comfortable with it. Okay, on this one, we already introduced this. This is technically really any type of physical contact force. So one thing touching another. Now, one of the things to note on this, in fact, that's actually going to lead into what I'm going to write next. Normal forces are something that happens so commonly in our universe that the technical term is normal force, but there's a bunch of easy ways to refer to it in modern and regular language. And so I'm going to put a few of them out there, and while this isn't a comprehensive list, it's words that you can look for that are using day-to-day words that give you an idea that you're actually dealing with a normal force. So common ones that we might have on this are going to be a push or a pull. I can push on a door or pull on a cart. Both of those are me physically touching it and interacting with it, so that's a type of normal force. I can also touch something. I can touch the wall. I can also hit something. I can hit the wall. Maybe I'm having a bad day, but there are better ways to express yourself, Sanchez. Okay. And I'm going to put ETC on this because, etc. Like, seriously, there's a bunch of different ways that you could actually refer to a physical contact force. There's also something like hold. I'm holding a ball, that sort of thing. I'm not going to go through the full list on here, but this gives you an idea of ways that it might be implied in a word-based question without us saying, you apply a normal force onto an object. These are some good examples that give you a clue that you're dealing with a normal force. But anytime one object is physically in contact with another, they're sharing a normal force. Okay, first off, our notation. The normal force, capital F, subscript, usually a capital N. I'm going to put a smiley face next to this because there is another commonly used one as just capital N, sometimes with a vector sign. I'm going to put a frowny face next to that. If you are not in my class and you are in someone else's class and they have you use capital N, I'm sorry. In this case, we measure forces in newtons, so it gets super confusing to have one capital N for a force, and then you'd have something like capital N equals 30 capital N. It's a mess. And for the AP exam, they will preferentially use this, F sub N. I guess I forgot to mention it in the previous video, though I did mention it at the beginning, that some older professors or older styles use a capital W instead of F sub G for the force of gravity. This is actually in keeping with the same thing where they use one capital letter to represent it. I don't like this. Avoid using this if you can. I'm seriously recommending that you avoid it. This is the one that we will be using with my materials, and please, 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 if you are my students, use this notation. Even if you're not my students, I recommend using that notation. If you're taking the AP exam, as a reader for the AP exam, it will make it much easier for us to understand what you're doing if you use this notation, and this is the notation that is used by the AP exam. That doesn't mean you have to use it to get credit, but the more clear you can be to the grader, the easier it is for you to get those points and get the points that you've earned. Okay, here's the other thing that might result in a frowny face. The other thing about it is the normal force has no equation. We're going to have a few forces on this list that there isn't an equation. And the reason there isn't an equation, there was an equation for gravity because gravity is a force that follows some rules that can be expressed mathematically, and therefore we can predict exactly what the force of gravity is going to be if we know the local effects of gravity, the local gravitational field strength, and if we know the mass of the object. When it comes to a normal force, I can push on the wall with 5 newtons, or I can push on it with 50 newtons. I can kind of choose how hard I push, at least within the realm of what I'm actually capable of doing. I'm not able to apply 50,000 newtons on the wall because I'm just not strong enough or not in a position to do that. So I'm not saying it could be literally anything, but there's no equation that we could use to predict what that force will be. So that's the first thing that you actually want to note about this. On the upside, there are some options. Usually, one of 2 things will happen. So usually, even though we don't have an equation for it, 1, you will be given the value. So if we talk about a normal force, we might say I apply a force onto the wall, and it has a magnitude of 10 newtons. I might just straight up give you the number. And therefore, you wouldn't need the equation, because there isn't one, but you wouldn't need it because you'd actually have the number. The other possibility, and this one is also equally likely, you're going to have probably about half of problems we'll give you the number, half of problems we are going to ask you to solve for it, but you may ask, well, how can I solve for it if I don't have an equation? We're going to see this multiple times. We can solve for the normal force with Newton's second law. And that's one of the things that we're going to see in our lesson today. Okay, in fact, we're going to jump right into that. Example number 1. I'm going to show you how to actually go about this. Okay, keeping with this, we've got, props. Great. A common feature in questions dealing with this is one of these, a bathroom scale. Now, I can put the scale on the ground and, let's see, I don't want to get too close to the camera because it might offset it some and cause it to focus on the wrong thing. I'm trying to be cognizant. I really hope that it's maintaining focus so that you're not seeing a blurry picture on here. But my production quality is not the highest. My apologies. So I'm going to stand on this scale, and it reads a little above 160 pounds, which we had talked about in our previous lesson. The mass of Sanchez is 72 kilograms, about that anyway, and that equates to about 160 pounds. We also found from our last lesson that the force of gravity on Sanchez is 706 newtons. Or, if we're approximating it with 10, then we would say that this is about 720 newtons. So, in this case, going back through that real quick, force of gravity is our mass times the acceleration due to gravity. On my exams and the AP exams, it's common for you to use 10 meter per second squared or Newton per kilogram. And so if this is, I apologize, let me change this to a 72 kilograms, then we would end up with 720 newtons. I almost wrote kilograms. Pay attention, Sanchez. There's a scale there. Okay, so this would read 720 newtons. Okay, now the first question that I have for you on this is, what force does a bathroom scale, does a scale actually measure? I'm pausing for a moment on this because most of the time students will immediately respond that it measures the force of gravity, but it doesn't. If I set this on the ground here, and let me move it slightly over some, I've got another table over here that I've got. It currently reads 160 pounds, but watch this. I'm going to take my hand, I'm going to put it on the wall here. Now it reads 120 pounds. And by doing this, I can't quite hold myself up like this. There we go, arm day. It reads 0. I can lift my legs up. And does that mean that gravity just forgot about me? No. In fact, the other thing that I can do is this. I can take this and I can put it up against the wall, and I can push on it, and this reads 40 pounds. It reads 70 pounds. That's not the force of gravity. The first thing you need to understand for a lot of the problems that we're going to take a look at is the scale doesn't read the force of gravity, It reads the normal force, how hard you're pushing on the scale. So here's my question. What should the normal force, or what should the scale read? In other words, what is the normal force applied onto me on flat level ground here in the classroom? Now, most people think that the scale reads the force of gravity on you, and we're going to find that that's not necessarily wrong. The number you see is the force of gravity on you, in many cases, but not all, but it's not actually measuring the force of gravity. So let's see what we've got. So for me, I'm standing here in the classroom on the scale. There's my sweater, my little purple hula skirt. And I want to know what the reading of the normal force, what the reading of the scale is, which is actually measuring the normal force. I'm going to push this out of the way before I trip on it and kill myself on camera. So, here we go. Normal force. Now, our immediate response on this would be, okay, I need the equation for a normal force, and that's where we get sad face because we have no equation for it. So I'm going to show you, we were not given the value, so here we are in option 2 where we're going to use Newton's second law to solve for it. Well, if I'm going to apply Newton's second law is the sum of forces equals our mass times our acceleration. Okay, great. So if I want to apply that, forces cause accelerations, and once again, I'm going to emphasize this every single time, at least here at the beginnings of the lessons, we need all the forces acting on the object, not just one. So we're going to draw a free body diagram. Okay, now you may be tempted to immediately put in the normal force because that's the thing you care about, but I once again heavily recommend you go back in your notes to the force list. Let's do this the proper way, because on the easy questions, it'll seem meh, like you don't need it. On the hard questions, I promise you it will help. So going down the list. Force of gravity. Is there a force of gravity while I'm standing on the scale? Well, yeah, I got gravity still pulling down on me. It would be really cool if we could get gravity to just forget about me. But unfortunately, or I guess actually fortunately, because I don't like floating around that much, there is a force of gravity and it is pointed down, just like it was before. Gravity pulls things downward. Normal force. Is there anything physically in contact with me? Yes, there is. The bathroom scale, or regularly the ground, and it is pushing on me. I'm in physical contact. My feet are in contact with the ground. And which way does it push? It pushes up because the ground is holding me up. So I'm going to put this as my normal force from the ground. Okay, great. With me standing here, other than my feet on the ground, I'm not touching anything else, so that is the only normal force. In some problems, you may have multiple normal forces. If I reach out and I touch the wall, I now also have a normal force from the wall. We're going to keep this simple for now. I just have the normal force up. So we're done with normal force. Force of friction. Well, I am in contact with the surface, but we're going to find in our next lesson that friction is really about like either sliding or trying to keep me from sliding. If I'm standing still on flat level ground, I'm not trying to slide and I'm not actively sliding, so I won't have a force of friction. We're going to see that in the next lesson, but take my word for it that we don't have a force of friction right now. Okay, next one. Force of tension. Okay, are there any strings or wires connected to me? Nope, so no force of tension. Okay, next up. Drag force. Well, I don't actually have to worry about air resistance, and as we've said before, we ignore it unless you're told to include it. So no, we don't have a drag force. Force of thrust. Do I have any rocket engines on me? No. And again, you may be asking yourself, that's kind of silly, but I'm setting you up to go through that list so that you can always be certain that you've got all the forces acting on an object. Now, at least for the online lessons, I've included spring force. I do not actually have any springs attached to me. We are now at the bottom of the list, and therefore this is my complete free body diagram. Trust me, as we start getting more and more complex questions, going down that force list is your best way to make certain you don't make a mistake. Okay, now that we've got this, here is my free body diagram, and we can apply Newton's second law. As a reminder, the next thing that I see for new students, their first problem is knowing when they are done with the free body diagram and that they found all the forces. That's what the force list is for. And then the other thing that I see a lot of students run into is when they complete their free body diagram, that's a nice looking free body diagram, but they don't know what to do next. The entire point of a free body diagram is to apply Newton's second law. So after you draw the free body diagram, go straight to writing out Newton's second law. This time, we don't have just one force, we have multiple forces, so we need to add them up. I'm going to look at my free body diagram and include all those forces. One of the forces I see is a normal force, but remember, these are vectors. In this case, it is up, so this is a positive. I've also got a force of gravity, but it is down, so I'm going to put a negative. These are all of my forces, so I am done with setting up my forces. This is, when I add these together, this is my sum of forces. Equals my mass times my acceleration. Okay, so I'm going to fill some of this in. We've got a normal force minus the force of gravity on Sanchez was, I'm going to use the rounded number and say 720 newtons instead. Remember, that's 72 kilograms and using 10 Newton per kilogram or meter per second, as we would on the AP exam. That's going to be equal to my mass, which is 72 kilograms, times my acceleration. So, look at me right here, right now. What is my acceleration? Well, I'm at rest, and I remain at rest. So my acceleration is 0 meters per second squared. If you said 9.81, well, that's if I were falling, but I'm not falling. And I want to pause for just a moment here, because if you're not one of my students, your teacher might be doing things a little bit differently. They may have started with this, and they didn't show you the gravity one, which is perfectly fine. One of the ways introductory physics is often taught is they'll take students and show them a bunch of what's called balanced problems, like this, where your acceleration is 0, and you have that your sum of forces is equal to 0 because your acceleration is 0. And then they'll solve a bunch of those where the forces are balanced. Some people call that a Newton's first law thing. I don't like that approach. I like going straight to just understanding Newton's second law. So in my class, some of our problems, the objects will have 0 acceleration, standing still, remaining at rest, or moving at constant speed, as we will see in our next lesson. But you have to stop and think, what is the acceleration of the object, if you know about its motion? Well, I'm just standing here, doing nothing, and so my acceleration is 0. Okay, so I put in 0. So 0 times 72 gives me our normal force minus 720 newtons, which is my weight, is equal to 0. In this case, newtons, because kilogram times meter per second squared gives me a newton. Although it looks a little weird to have 0 newtons because it looks like I'm just saying on. But in this case, I have 0 here. I can now solve for my normal force, and I get that my normal force, I add the 720 over to the other side, and I find that my normal force is equal and opposite to the force of gravity. But once again, not because of Newton's third law. They do not have to be equal and opposite. They have nothing to do with Newton's third law because they're two different types of force. In this case, they happen to be equal and opposite because my forces are balanced, which happens a moderate amount in our universe, but not always. In this case, here's how I can solve for a normal force. Okay, that's great. So the scale, in this case, would read about 160 pounds. Okay, great. The other one that I want to explore is this, example 2. Now, this is an experiment that you can actually do if you have access to a bathroom scale and an elevator. Go get in an elevator, and then you set it on the scale on the ground, you step on it, and you press the button to go, say, up or down, depending on where you're at. And the elevator, with you in it, will change its motion. Now, it will have to accelerate to get it moving. We're going to say that I get in on the ground floor, I hit the button, and the elevator, with me, accelerates upward at a rate of, let me check my notes, 1.5 meters per second squared. So here we go. Example 2, elevator. And so in this case, I'm going to have a little elevator. It's going to have a string attached to it or a cable pulling it up. Some of them do, some of them don't. You might think of force of tension, but we're going to be looking specifically at me on the scale. So, while there is a force of tension involved in this problem, I'm not going to draw it in on my free body diagram because the rope is not attached to me. That's a preview of things to come, but I want to lay that out in case you're jumping at the gun and saying, hey, we got a string on this one or a rope. But here's where we want to keep track of what we're looking at. What I would like to know is this. What does the scale read? Or, as we've established, the scale reads my normal force. Okay, great. So on this, oh, I apologize. I hit the button, and we have an upward acceleration of 1.5 meters per second squared. That is at the very beginning when the elevator starts moving. Now, most elevators will accelerate for a short amount of time, get up to their top speed, and then go at a constant speed. So when you're in the elevator, if you test this, you'll actually see the needle kind of go up while you feel like you're being squished some. That's the elevator speeding up. And then it'll go back to normal, and you'll feel normal, and that's because you're actually going at a constant speed. Then it'll flick again when you get towards the top and begin slowing down, but I'll let you collect the data on that. Okay, here we go. Here's what I'm going to do. I've got me in an elevator, and we're going to ask what the scale will read while I am accelerating upward with the elevator. So on this, once again, we are not given the normal force, so we're going to have to solve for it. So I'm going to draw a free body diagram so I can apply Newton's second law. Okay, so on this, going down our list, once again, we have a force of gravity downward, Fg. We have a normal force of my feet on the scale holding me up. And in this case, pushing me upward, because that's the thing that's touching me to make me go upwards. There is nothing else that I am touching other than the scale right here. So that's my only normal force. I'm not sliding to the side. I really hope this elevator isn't moving laterally. So we have no force of friction. When we come to force of tension, here's where I said if you're not paying close attention, you might go, hey, there's a rope involved with this, but the rope is attached to the elevator, not to Sanchez. And here's where, when you start working with multiple objects, you have to really think which object you're looking at. So while there's a rope involved in this problem, it is not on Sanchez, and therefore, I'm not going to include it on my free body diagram of Sanchez. Okay. So we dealt with force of tension. Next one up is drag force. In this case, we're going to ignore air resistance as we usually do, and the air resistance would actually be outside of the elevator, not in the elevator anyway. Okay, let's see. Thrust. We don't have any rocket engines, at least on me. Maybe this is a rocket-powered elevator, but once again, even if it did have rockets on it, they would not be attached to me, so I would not draw the force of thrust on it. And lastly, springs. We're going to say that I've got no springs attached to me. In fact, I don't see any springs, but technically you could argue that's what's in the scale. Don't worry, we'll learn about that later. But in this case, no springs, and therefore, we've reached the bottom of our list. Here is my free body diagram, at least based on the knowledge that I've got. Okay, so in this case, I can now apply Newton's second law. Once again, we have positive normal force minus the force of gravity equals the mass times the acceleration of our object, looking at me. I do not know the normal force, but that's what I'm after, minus 720 newtons, that is the force of gravity on me. We found that before, that is my mass, 72 kilograms, times the acceleration due to gravity, rounded to 10 meters per second squared, in accordance with what they normally do on the AP exam. My mass is 72 kilograms, as we just said, and now my acceleration is not 9.81, and it is also not 0. I am accelerating upward with the elevator, so I have an acceleration of positive 1.5 meters per second squared, the same as the elevator. At least I really hope it's the same as the elevator, because if my values are different, then I'm falling out of the elevator. So in this case, I get my normal force minus 720 newtons is equal to 72 times 1.5 with appropriate units. 108 newtons. Now, this is not 0 because I do have a net force being applied to me, which will result in my mass being accelerated by this amount in the direction of the net force. In this case, that's just explaining conceptually what we're working with. We want to solve for our normal force, so this is minus 720, so I'm going to add 720 to both sides, and we find that my normal force will be equal to, I guess that is 828 newtons. You will actually see a spike upward when you accelerate upward because the scale has to push hard enough on you to keep you from falling down. It's got to counter out gravity. And it's also going to supply enough additional force to accelerate you at 1.5 meters per second squared. And by you, I mean me, I guess. So on this, this would come up to approximately 185 pounds, at least with my numbers. And so on this, if I were in an elevator and while it's accelerating upward at 1.5 meters per second squared, I would actually see the needle tick up to 185 rather briefly, and then it would go back to normal when we reach top speed. Okay, the last thing that I'm going to say on this has a title. this concept. It is called apparent weight. Now remember, in our last lesson we found that the weight was the force of gravity on you. The apparent weight is basically how heavy you feel. I'm going to put feel in quotation marks because this isn't a, oh man, I ate an entire bag of Doritos, I feel pretty heavy. Instead, this is a sort of thing like with the elevator. When you press the button, when you accelerate upward, you feel squished, like you're being pushed down some. You actually feel a little heavier. Are you heavier? No, your force of gravity is unchanged. Your weight stays the same. Gravity has not changed on you. You feel heavier because of what's happening. It appears that you are heavier. It feels like it. It seems like it. That's where we get apparent weight. That's a different form of the word appears. It's what your weight appears to be, what it feels like. In this case, the apparent weight, emphasizing what we've got, if you're asked about the regular weight, they're talking about the force of gravity. If they ask or comment about the apparent weight, they're talking about the normal force holding you up, or whatever that object is, up. Now, you can have it where the apparent weight is heavier, is greater than your regular weight, just like here, when I accelerate upward. And then when I get to the far end of my elevator ride, I'll leave that as an example for you, what happens when I slow down? Well, we'll set it up. I'm in the elevator, just the same as I was before, except this time, we have an acceleration downward, let's say of negative 1.2 meters per second squared. Now, negative is because we have an acceleration downward. If we're moving upward, velocity up, acceleration down, we are going to slow down. That's how we slow down to come to a stop at whatever floor we want so we can get off. You might have a different acceleration slowing down, and a reason for that is there's one mechanism, usually the rope, pulling you up, and a different mechanism, usually some brakes, that slow you down. So it makes sense that you may not have the exact same number for both speeding up and slowing down based on how these things work. In this case, I will help you set this up. We still have our normal force minus the force of gravity is equal to our mass times our acceleration. But remember, acceleration is also a vector. Same with the forces. So we would have our new normal force, I could call that Fn prime, we're going to see that more as we go through, but would be Fn prime, our new normal force, minus 720 newtons is equal to 72 kilograms times negative 1.2 meters per second squared. This is kilograms. Multiply these out, and now this will be a negative number. When you add this over, we will have a normal force less than 720 newtons. When you get to the top and you're slowing down, you actually feel a little bit like you're not quite floating, but you feel a little lighter. You appear to be lighter, apparent weight. You will find that your normal force is actually less than the normal value, which is 720 newtons. For me, we would actually see that I would, while slowing down under these circumstances, I would actually feel a bit lighter, and it would correspond to a weight less than 160. All right, I'm going to leave this to you as an example that you can solve as a challenge. But this is all the stuff that we wanted to talk through about the normal force. Next up, in our next lesson, we're going to be taking a look at friction.